In this video, we are going to discuss the Complex Laurent series. This is our overview slide, which we'll spend about 5 minutes on before we go over each of these topics in more detail and more examples. We are going to start by reviewing what your book calls the basic Taylor series, and that's the Taylor series for the function f of z equals 1 over 1 minus z. You can see there's a singularity at z equals 1, so the radius of convergence for this, if we're centered at 0, is absolute value of z is less than 1. Then we can expand this using a Taylor series, and it becomes equal to 1 plus z squared, which is the summation of z to the n. So this is the basic Taylor series. It is one that you will use a lot, and you should definitely memorize. The next topic in your book is discussion of the Complex Laurent series and development of the Complex Laurent series. And it's quite a long discussion, but even towards the end, your book says, and after a bunch of calculations. So we're going to just go over some highlights because the real work comes later. But it's important that you kind of know what this is about because it has some clever things and things you want to be aware of. So the idea is if we have a series and we want an expansion of a function, which has a singularity at a point, we're going to call it A. And so we want a series which is valid in a region outside a singularity circle of A. So over here, if we have this curve C here, and we have A, which is a point of singularity, for the Taylor series, we can only evaluate or expand inside this singularity circle of A. So if we want to do something here with C, we cannot use the Laurent series because we cannot use the Taylor series because the Taylor series requires everything on the curve of C and inside the curve of C is analytic. But if A is a singularity point, then f of z won't be analytic. And that's where the Complex Laurent series comes in. And what we end up doing is we make a new curve C, and it's this curve that goes around. It doesn't quite close, and then it goes over, and then it goes around in the other direction, and it closes over here. But you can see then C encloses this yellow shaded region, but it avoids our singularity A. And then by path deformation, we can bring these two endpoints closer and closer till essentially we have this annular region here. And that's what we will be using to integrate over our curve C1 and developing the formulas for our Complex Laurent series. But here is the formula. It's these coefficients times z minus z naught. And for Laurent, the nth power over here can be positive or it can be negative. So I've written it this way. We have positive powers of n, and this is where we're analytic. And this looks like a Taylor series. In fact, it is a Taylor series. Over here, we have negative powers of n, so it's in the denominator. And this is often called the principal part. This is often called the analytic part since this is analytic. This is called the principal part. And then we have this formula which we will kind of develop or sort of pseudo-develop, will hand-wave develop for the coefficient C of n. Do you remember how when we looked at the Taylor series, we used the formula for the coefficients, and then we did it a second way by using the basic series over here? That's the same thing we're going to do for the Laurent series. Mostly these coefficients, they get to be quite, the integral gets to be quite a lot. So what you'll find is really the way you're going to do Laurent coefficients is by using the basic Taylor series, which is why it's a good idea that you just know it, that you memorize it. And what we wanted was a Taylor series expansion of f of z equals 1 over z minus a. We want to put it in this form of 1 minus z. So on the bottom we have a z, that's great. On the top we have a 1, that looks sort of similar. But we have not just an arbitrary constant a over here in the denominator, we have a 1. So we divided the numerator and denominator both by negative a. And you can see that produced a 1. And then this z, this was a function of z, and that's good. That was okay in the denominator. We factor out the minus 1 over a, So we have exactly this form, 1 over 1 minus some simple function of z. So what we can do then is for this 1 minus 1 over z over a, we can plug in z over a into our basic Taylor series formula and get an expansion. So that would be 1 plus z over a plus z over a squared plus z over a cubed. And of course, we have to still keep our multiple of minus 1 over a in front. But now, if we want convergence for z greater than a, for this function here, we need a Laurent series. And what we are going to do now is looking at this formula. Again, at the bottom we have a z and an a. So our choices are to divide everything by a or divide everything by z. So we're going to try dividing everything by z so that at the bottom we get a over z. And in this case, if z is greater than a, this is still less than 1, and we can apply our Taylor series formula here, and we get 1 over z from this, and then plugging in a over z into our basic Taylor series, we have 1 plus a over z squared, etc. So this is the Laurent series expansion here. And we have a couple of other examples that are really good to go through. Last, we'll have this final example for the Laurent expansion about z naught equals 0 of minus 1 over z minus 1, z minus 2. And there are two singular points you can see where we have division by 0 at z equals 1 and z equals 2. So I've drawn our singular circles here. Here is for our singularity at 1, our singularity at 2. So there are 3 points where f of z is analytic, or 3 areas where f of z is analytic. The first is when we're in this inner circle, when z, absolute value of z is less than 1. The second is when we're in this annular region where we're between the two singularities. So absolute value of z is between 1 and 2. And finally, when we're outside, that is, absolute value of z is equal to 2. So this is an involved problem with 3 sections, and we will do that in this video. And I guess sort of finally, this section of your chapter has classifications of singularities, but I decided to make that a separate video, so that will be in our next video. So that's our overview. So now we can go back and start with basic Taylor series. Here is our formula for our basic Taylor series. So f of z equals 1 over 1 minus z, and that is equal to the summation of z to the n. And remember, we use the series expansion of this basic Taylor series to find representations of other functions. And what we can do is we can, and this is the one that your book uses a lot, so that's the one we're sticking with, replace this z here with a simple function of z, something like 3z or z minus 1 or I times z or z divided by 2. The other thing that we might do is multiply the entire equation by a value. These other two things are totally valid, but we don't use them that much, or your book hasn't shown me that they use them. So we're not really going to cover them, but I have it here just for the sake of being complete. So how can we use this? Let's say we have the function f of z equals 1 over z minus a, and we want a Taylor series expansion, but we don't want to do the trouble of calculating all the derivatives and the coefficients. So instead we're going to use our basic Taylor series. So we want our function f of z, 1 over z minus a, to be in this Taylor series, basic Taylor series form, except that z can be a simple function of z. And when I look at this, this looks a lot like 1 over 1 minus z, except that here we have a constant a as opposed to the constant 1. So what I'm going to do to get rid of the a, I'm going to divide everything by minus a. So I divide the numerator by minus a, and I divide everything in the denominator by minus a. So I'll get minus 1 over a in the numerator. The denominator now is going to be, right, minus z over a, and then minus a over a, that will give me 1. And now I can swap the order, and I can also factor out the 1 over a. I swap the order here, so I have 1 minus z minus a. So I have exactly the correct form that I want. So I still have my, this part here, my 1 over z minus a. Now I can plug it into my basic Taylor series, except substituting for z, I'm going to substitute z over a. So I'm going to get 1 z over a plus z over a squared plus z over a cubed. And now for the function, I still need to multiply by minus 1 over a. So I have minus 1 over a times my series, which gives me this series over here. Also, once I have this, I can also decide, instead of expanding around 0, which is what I did here, I can expand around z equals z naught. And the way I do that is for f of z equals 1 over z minus a, I introduce a z naught to my z by saying z minus z naught in the denominator. But of course that means I need to add a z naught also in the denominator. So this is how I do this. And now if I look at this and I compare it to my Taylor series, which is up here, I have my 1 on top. That's great. I have a simple function of z. This is just z minus some constant z naught. So I have a simple function of z. But again, instead of the 1 over here in the denominator, I have a constant a minus z naught. So I'm just going to divide the numerator and the denominator by my constant a minus z naught. Very similar to how I did up here. And then I get my function. And I can then expand this, substituting z minus z naught over a minus z naught for z in my basic Taylor series. That gives me the series here. I have this multiplier in front, and this is my final series. We will be using this technique of using the basic Taylor series, both when we develop the formula, the integral formula for the complex Laurent series, and also in the same way, the exact same way we did this for the Taylor series, we're going to use this in the Laurent series, except that because there are singularities, we have to watch for the singularities. That's the added complication of Laurent. Our next topic is to look at the complex Laurent series. And here is the formula or the form of the complex Laurent series. It's a summation from n equals negative infinity. So first we want to know that we can have negative n terms. So n is equal to negative infinity to infinity. C of n, some constant multiplier, our coefficient, times z minus z naught. Again, z naught is the center of our expansion, raised to the nth power. So I'm going to separate out, because this is how I like to look at it, although your book doesn't separate it out this way. This is just what I like. I like to separate out my positive n this way, so n goes from 0 to infinity, an z minus z naught to the nth power. So that's n equals 0 to infinity. And then for the negative exponents, I still like to have n goes from 0 to infinity, but now n is in the denominator. That's how I reflect the fact it's a negative exponent. And I like this because it's just more visual to me. This is often called the analytic part because this doesn't have the zeros or the singularities that the principal part has. So this is called analytic, and this is called the principal part. So the coefficients and region of convergence depends upon f of z, obviously, and the expansion point, z naught. And then the Laurent series is useful when you want an expansion that converges in a region surrounding a non-analytic point of f of z. So remember, for Taylor series, it needs to be analytic everywhere on your curve and inside. Here, the Laurent series is trying to be able to give you other regions that the Taylor series cannot reach. So for example, if we look at this picture here, suppose we want to generate a series expansion of f of z equals 1 over z minus a. So obviously here a is a singular point, and we're going to expand it around z naught. So this is our picture. We have z naught here, and then we have this point a, which is singular. For a Taylor series, in our last video, we expanded this inside the circle. Absolute value of z is less than a. So we were able to do our Taylor series inside this circle, singularity circle. But now suppose we want an expansion which is valid in a region outside this singularity circle of A. So maybe this region over here at C prime. We cannot use a contour like C over here, which contains A. So inside of the contour, we have A, because the Taylor series requires that f of z be analytic at all points inside C. What we are going to do then, because we need a contour that does not include A, is we're going to consider a new contour. And in the yellow region, interior to C, this is our new contour C, the function f of z is analytic. So let's take a look at C. So C is kind of a combination of two circles. So it's this path here, there's a little straight section. We have the circle that goes around, but it doesn't close, and then it comes across, and then there's a circle that goes in the opposite direction, and this is our contour. It encloses this yellow portion here, and you can see it totally avoids A. Now this contour is a valid contour to use the Cauchy integral formula, because f of z is analytic everywhere inside this contour, so we can use the Cauchy integral formula, and then we can find our coefficients for our Laurent series. And now finally, using contour deformation, the two straight end pieces of C, that's this little piece here and this little piece here, can be brought arbitrarily close together so their contributions cancel because they're in opposite directions, right? Over here, the top straight piece goes outwards from the origin, whereas when we come over here along C, the straight line is going inwards towards the origin. Theoretically, I would have drawn them the same length, and they'd be really arbitrarily close to each other, like this line here, and this would go all the way over here till it almost touched, so they would cancel each other out. So what you're going to get then is that we have the circle C1, the outside circle, and the inside circle, which is in the opposite direction, and we've canceled out this straight line portion. And then we introduce this negative sign so that we can change C2 to be in the same direction, so that now they're both counterclockwise. And I wanted to show you this trick of being able to integrate inside some contour when you're trying to avoid some point where it's not analytic, because this trick of making this weird circle that just encloses everything but A is used everywhere in complex analysis. So many circles in complex analysis, and then you close it and then you have this annular region. Very common trick. And again, we're concerned with it for the Laurent series because this is the formula that allows us to find the coefficients for the Laurent series, these integrals here. So now what we have is we can integrate f of z, and these are the two contours we have here. And then we can expand about z naught, so we can introduce our z naught, much like we did in the previous example of 1 over z minus a. To expand around z naught, right, we introduce a z naught, but then because we subtract a z naught, we need to add a z naught. We use the basic Taylor series expansion. Again, we have a function of z, but which one's the function of z? I'm sorry, this is our function of z. This is our z prime. Z prime is something out here. So this is a constant. We need to divide the top and bottom by the constant. And here we have f of z divided by the constant. And then we can plug this into our basic Taylor series, and then this is what becomes of our integration. So here is your integral over C1, this outside circle, integral over C2, your inside circle. And I realize I'm going over this quickly because this is not the super important part of the video for you to be able to work your problems. But you are familiar with all these techniques, so if you look at it, you should be able to understand it. And again, here's where we left off. Our f of z then is our coefficient, which is written here, z minus z naught raised to the n, and then our second integral over c2, again, our coefficient over here, which is rewritten here, z minus z naught to the n. And remember, these coefficients are valid in the annular yellow region here. And thus, this region can be expanded by shrinking C2. So we can shrink it down all the way up to A, the radius, the singularity circle for A. Oh, here it is, until it runs. And then we can also expand C1 until it runs into another singularity. And then we'll be keeping f of z analytic between the two circles. So once we've determined the max contour for C2 and the minimum contour for C1, the expression for the coefficients can be combined. And note, if f of z is analytic everywhere inside C, all Cn for n less than 0 must be 0. So that means, if everything is analytic in here, then we don't even have this principal part, because we can basically fall back to a Taylor series, and that's what this last comment is. And the Laurent series degenerates into a Taylor series. Next is to determine the coefficients of the Laurent series expansion of f of z equals 1 over z minus a, our familiar example, plus 1 over z minus b, also our familiar example, but with a different coefficient. So being able to add them together, this is a very common example, and it's equal to, when you multiply everything out, 2z minus a minus b over z minus a, z minus b. To start, we're going to note that f of z is analytic everywhere except at z equals a and z equals b, and the Laurent series now is going to be expanded around z equals z equals z naught. So here is our picture. We have our z naught, which we're going to expand around. We have a singularity a and a singularity b. And in this figure, we assume that a is closer to z naught than b, but it generalizes either way. So for this example, the contour C used for determining the Laurent coefficients, when we plug it into our integral here, must be centered at z naught, but can be located in 3 general regions. So we're going to break up our problem into 3 parts. First, it could be inside the small singularity circle, that is the singularity circle of A. So we could be in this region here. 2, we could be between A and B singularity circles. In other words, we can be in the annular region here. Or 3, we could be outside the large singularity circle out here. So the 3 situations will be treated separately. Now this is where I'm going to tell you I'm not going to worry too much about the details of using this integration thing here in order for the 3 different cases, because even your book, by the 3rd case, it says, well, after a bunch of calculations. And so I think the point is not so much that we go through all of these things here, except that, 1, maybe your book has you kind of memorize this formula for this case. But what I'm going to do instead, I have kind of the points outlined from your book and the pictures. And rather than go through this example where we calculate with the integral, the coefficients, I'm going to focus on using the basic Taylor series expansion, because that's probably the more common and easier way to solve these problems. But even with using the basic Taylor series, we're still going to have the 3 different cases. The first one being inside the small singularity circle, this portion here in yellow. But your book does outline this with the integration, and here is the answer for this first section. 2, between the A and B singularity circles, again, this yellow part, and this is the result. And 3, outside the singularity circle. So the thing to know is, to determine the coefficients of the Laurent series expansion, you have to divide this into 3 portions, because you're using basically different curves to do your integral, and your your places where you converge to a solution are going to be different depending on which of the 3 cases you're in. So again, your book does this using the integral, and then it gives you a final formula, and maybe they'd like you to memorize the formula. So you'll have to know from your class if that's what's appropriate. But I also have examples where you don't really memorize the formula. We'll go through the 3 cases, but instead of doing the integral, we're going to use the basic Taylor series expansion. Which brings us to our 3rd topic, Laurent coefficients using the basic Taylor series. This is really the way you're going to do it, not so much doing this integral. Our example is to find the Laurent expansion about z naught equals 0 of f of z equals 1 over z minus a. And it may be that you realize, and this is a good thing, that we work this problem for Taylor series for convergence of absolute value of z is less than a. You can see here that at a we have a singularity or a division by 0, so we had to expand, but we had to have z, this z here, in the singularity circle of a. Because we've seen this example before more than once, I will leave the work done here, but we will not go over it again. So our new variation on this problem is we want convergence for absolute value z is greater than a. In other words, we don't want our z to be limited just in this little circle here. We want our z to be somewhere out here, perhaps. Which means we will need a Laurent series with possibly some negative n powers of n. But let's consider when we were working with our f of z, and then we converted our function 1 over z minus a to this form here, so that we could have 1 over 1 minus z over a. In this case, when z is greater than a, our z over a now is going to be greater than 1. And because it's greater than 1, we can no longer use this basic Taylor series because this series has a singularity at 1. And for a Taylor series, we need to stay inside the radius of convergence. And that would require absolute value of z to be less than 1. So we need to do something else to get our Laurent series. And in particular, when you look at f of z over here is equal to 1 over z minus a, when you want to convert to the form of this basic Taylor series, 1 over 1 minus z, you need to get a 1 instead of, you need a 1. You need to introduce a 1 in the denominator. And you can do that either by dividing by a, as we did here, or you can divide everything by z. And since we already said why a wouldn't work, is because by then our basic Taylor series won't converge, we're going to try dividing by z. That is, I'm going to divide my numerator and my denominator, everything by z. So on top I'm going to get 1 over z. Here z divided by z will give me my 1, and my a divided by z will give me a over z. So now if you look, I can factor out my 1 over z, and now I have the form 1 over 1 minus some simple function of z. And that's going to be equal to my 1 over z, plugging in a over z into my basic Taylor series now gives me a over z to the 0 power, which is 1, and then a over z squared, a over z cubed, so the powers of a over z. So one more note that's very important. To use the basic Taylor series on 1 over 1 minus az, 1 minus 1 over az must be analytic. That is, the absolute value of a over z must be less than 1, right? Because we're using this basic Taylor series expansion, which depends on the absolute value of z being less than 1. Here we're substituting a over z for z, so that translates to absolute value of a over z must be less than 1. So that, again, we can plug in and use the basic Taylor series, which we did right here. So since we are working in the region, our first assumption is that we wanted to be beyond this, the range of convergence for the Taylor series. So we assumed that the absolute value of z is greater than the absolute value of a. So since we're working in this region where absolute value of z is greater than absolute value of a, we know that the absolute value of a over z is less than 1. So our series here converges, and we're all good. Your book often asks you for the coefficients, which I'm not sure why, because really now you have the whole series. But okay, so if they want the coefficients, that's what's in front of the z minus z naught. In this case, we're expanding around z equals 0. So in front of the z term. And remember, over here, we have no terms wherein the exponent on z is greater than or equal to 0. So Cn is equal to 0. And then our coefficients in front of our z minus 0 with negative n exponent, in other words, the z to an exponent in the denominator. So for these negative exponented n's, you can see the coefficient is 1a squared, and it lags behind n by 1 unit. So the coefficient then is a to the minus n minus 1 for n less than 0. And again, we have convergence as long as absolute value of z is greater than absolute value of a. One more addition to the problem of the Laurent expansion about z naught equals 0 of f of z equals 1 over z minus a. We just did the expansion here. So this is the work that we did from the previous slide. And now we're going to look at expanding about an arbitrary point z equals z naught. Since our Taylor series is going to have this form where we have our coefficients times z minus z naught to the n, we want to introduce a z naught as something of this form, z minus z naught. So here we have z, well, we can introduce minus z naught. So we have the exact form we want, but now since we subtracted z naught, we need to add back in a z naught. And then from there, we have, looking at this, comparing it to our basic Taylor series, we're going to, this is just a simple function, this is a simple function of z, so we're going to divide everything by z minus z naught, and then from there we can plug this in to our z to get our Taylor series expansion. So remember earlier when I told you we weren't going to go through this example here where we did the Laurent series by doing the integrating, actually calculating the coefficients? This is the example I'm going to do instead. So it's similar in that it's 1 over z minus a. Here a is negative 1, or no, a is equal to 1. And here 1 over z minus b, b is equal to 2. I have this extra negative sign, just I don't know why, for fun. Anyway, so this is the problem we're going to do, but instead of calculating the coefficients by doing the integration, we're going to use the basic Taylor series. And the problem is, again, minus 1 over z minus 1 times z minus 2. And this breaks down to two fractions, 1 over z minus 1 minus 1 over z minus 2. If you're wondering how we got this equation here, how we got the right-hand side of the equation, the answer is partial fractions. So now is a good time to review partial fractions, because if you don't remember, this is something you want to be able to do. Otherwise, if you're only given the left-hand side of the equation, you'll be kind of stuck. So let's start with negative 1 over z minus 1 times z minus 2. And what we want to do is break that down into a sum of two fractions, the first one with the denominator z minus 1, and the second one with the denominator z minus 2. Once you have this form written down, the only thing you have to remember, and everything else will fall out, is you're going to multiply both sides of the equation by z minus 1 times z minus 2. So here, on the left-hand side, you're going to get minus 1, and on the right-hand side, you're going to get, well, the z minus 1 will cancel out for the a term, so you're going to be left with a times z minus 2. And for the b term here, when you multiply by z minus 1, z minus 2, the z minus 2 will cancel out, and you'll be left with b times z minus 1. So here, just multiplying this out, on the left-hand side you have negative 1, on the right-hand side you have az minus 2a plus bz minus b. So grouping like terms together, you have az plus bz. There's no z terms over here, so that must mean it's equal to 0. And then also I factored out my z. So z times a plus b equals 0. Z is not equal to 0. That must mean a plus b equals 0, which means a is equal to negative b. Then the constant terms, what do I have? My minus 2a minus b equals negative 1. So a is equal to negative b. So this is going to be 2b minus b equals 1. And I'm sorry, actually this should be equals negative 1, right? Because the constant terms equals negative 1, which gives me b equals negative 1 and a equals 1. So when I plug that in, a is equal to 1, that's my 1 over z minus 1, and b is negative 1, which is my minus 1 over z minus 2. And again, I'm showing you this because this is important so you can do problems like this if they don't give you this right-hand side. You can see there are two singular points. One is at z equals 1, and one is at z equals z equals 2. So I drew these singular circles, z equals 1 and z equals 2. So f of z is analytic then when z is less than 1. It's analytic when z is between 1 and 2, so not equal to 1 or 2, but between 1 and 2, and then when z is greater than 2. So now we're going to have to work this problem for each section, for the z less than 1, another case for z between 1 and 2, and the third case for z greater than 2. So our first case for z less than 1, so we're analytic and we're in this yellow region here. And we're looking at 1 over z minus 1 minus 1 over z minus 2. We're going to start with this second fraction, 1 over z minus 2. And we want it in this 1 over 1 minus z form, so we can use the basic Taylor series. I made this z blue to kind of distinguish it from this black z over here. We want it in this form, but we want to remember to use the Taylor series, this 1 over 1 minus z, the 1 minus this z, which might end up being a function, a simple function of z, must be analytic. And so we need to keep this blue z, the absolute value, less than 1. For the basic Taylor series, the 1 over 1 minus z, which I have over here with the blue z, because now we're going to substitute z for some simple function of z. To get the 1 from the 1 over z minus 2, we can either divide everything by z, in which case the z over z becomes the 1, or we can divide everything by 2, in which case the 2 over 2 becomes 1. So those are really the only two moves we have here. And I want to try, because I always like to try just dividing by the constant. So I want to try dividing the numerator and denominator by 2. And I also know since z is less than 1, that's the region we're working in, z over 2, the absolute value of z over 2 must also be less than 1, which means when I substitute it into my basic Taylor series, I'm going to be good because my z over 2 is less than 1. So I'll divide my numerator by 1/2. Everything in my denominator I'll divide by 1/2. And actually, it looks like I divided by negative 1/2. So I have minus z over 2 plus 1. And then on the top, I'm also going to have a minus 1/2. Factoring out the negative 1/2, and then I have 1, and then I just switch the order, 1 minus z over 2. And remember, I'm happy with this z over 2 because I've already established it's less than 1, because we're in the region where z is less than 1, which means since this is less than 1, I can use my basic Taylor series. Next, I'm going to consider the other fraction, the 1 over z minus 1, and I want it in 1 over 1 minus z form. I can just multiply everything by negative 1, and then that will allow me to switch the order in the denominator, so 1 minus z. So this is how I can convert this to the correct form. And what you notice is now this z here, this is exactly this Taylor series form. So I don't have to worry about it converging. It's going to converge for absolute value of z is less than 1. The only thing I did is multiply by negative 1. So I'm going to be safe using the Taylor series here. So what I get is f of z is equal to minus 1 over 1 minus z, that's this portion, plus 1/2 over here, because there's a minus here and then there's a minus here, they cancel, make a plus, 1/2, 1 over 1 minus z over 2. So here I can just substitute in my normal basic Taylor series with a negative in front. Here I'm going to have my series, I'm going to have 1/2, and this portion I'm going to substitute z over 2 for z, and I get z over 2 raised to the n. There's some algebraic manipulation, and this is my final summation formula. Now I'm ready to do my next region with z, the absolute value z between 1 and 2. So I have this here, and it's this yellow annular region here. Again, I'm going to start with my second fraction, the 1 over z minus 2, and I want this in my 1 minus z, and I have it in blue to remind me this is actually a simple function of z form. But to use my Taylor series, my 1 over 1 minus the simple function of z must be analytic. That is, this z here, the absolute value, must be less than 1 because that comes from the requirement of my basic Taylor series. I'm going to consider what I did before, which is dividing the top and the bottom by 2. But now I'm also going to think, well, since z is less than 2, that's the region we're in, where z is less than 2 but greater than 1, then z over 2 is still less than 1, which means my basic Taylor series will converge. So I can still use the same form here, where I divide the top and bottom by 2, and I get my 1 over z minus 2 will be equal to minus 1/2, 1 over 1 minus z over 2. Now I'm going to look at the second fraction, which is 1 over z minus 1. And again, I want it in 1 over 1 minus z form. And I'm going to consider my negative 1 times 1 over 1 minus z. That's exactly what I did last time. But now this won't work because now I'm in the region where the absolute value of z is between 1 and 2. So in other words, this value of z here, I can't, if it's between 1 and 2, I can't plug it in to my basic Taylor series because the convergence for my basic Taylor series requires the absolute value of z be less than 1. So I can no longer guarantee that the absolute value of z is less than 1. So I cannot use this basic Taylor series to convert this here. What I can do is now divide the top and bottom by z. So dividing the numerator by z, I get 1 over z. By dividing the denominator, I get 1 minus 1 over z. So again, when you have something of this form, 1 over z minus a, you can get the 1 that you need for the basic Taylor series, either dividing by a, or you can divide by z, as we did here. So when I divide by z, I factor out the z, and I'm left with 1 over 1 minus 1 over z. And in this case, since we know z is between 1 and 2, we also know 1 over z is going to be less than 1. And since it's less than 1, we can plug into the basic Taylor series. This is going to mean f of z is equal to 1 over z minus 1 over z minus 2 for 1 over z minus 1. That's what we have over here. We're going to have 1 over z times 1 over 1 minus 1 over z. And then for the second fraction, we have that over here. We're going to have the minus 1/2, but since this is minus, we get a plus 1/2, and then 1 over 1 minus z over 2. So our the first term then is 1 over z, n equals 0 to infinity, and now we're going to plug in 1 over z to the n, plus now we have our 1/2, and then z over 2 to the n, and then we have this simplification, the algebraic simplification here. And now we're ready for our third and last case when z is greater than 2, which I've written here, and this is the graph, so it's outside z equals 2. Again, I'm going to start with the second fraction, the 1 over z minus 2, and again, I want this in 1 over 1 minus z form, but to use this Taylor series, we must be analytic, so this z, or the simple function of z, must be less than 1. Since z is greater than 2, z over 2 should be greater than 1. So I can no longer just simply divide the top and bottom by 2 because z over 2 is no longer less than 1, and we can't then use our basic Taylor series. And then, so we need to explore the other option. So the only other option over here to convert one of these into 1 is to divide everything by z. So when I divide everything by z, I have 1 over z in the numerator. My z divided by z gives me 1, and then minus 2 over z. I factor out my 1 over z, and I get 1 over z times 1, 1 minus 2 over z. And then also, I just need to verify that 2 over z is less than 1, because this is what I'm going to plug in to my basic Taylor series, which only converges with z is less than 1. So 2 over z, in this case, z is greater than 2, so that means this 2 over z is going to be less than 1. So I'm good. I'm going to look at my first fraction, 1 over z minus 1. I want it in that form. I can multiply by negative. and that will give me 1 over z, but in this case z is greater than 2, so I can't just use this form because I won't be able to plug it into the basic Taylor series. So what can I do? I can divide the top and bottom by z, and I get 1 over z in the numerator, and then z divided by z gives me my 1. My 1 divided by z gives me 1 over z. I'll factor out my 1 over z, so I'm left with 1 over 1 minus 1 over z. And in this case, since z is greater than 2, 1 over z is less than 1. So I'm good to go with the basic Taylor series. So my two fractions, my 1 over z minus 1 over z minus 2. I plug in for my first. I have my 1 over z times here. I plug in 1 over z into my expansion, and I get 1 over z to the n. Then I get my minus, where am I? Z over 2. This is my expansion. My minus 1 over z times the expansion of 2 over z raised to the n. And then I have some algebraic manipulations here on the summations. So finally, for our three regions, z less than 1, z between 1 and 2, and z greater than 2, we have these three solutions. And you can see they are different solutions. And that's because we have different convergences. To review what we've covered in this video, we covered the complex Laurent series. We started by reviewing the basic Taylor series formula for this particular function, f of z equals 1 over 1 minus z, and we found that that is equal to the summation of z to the n, and this is the formula that we want to memorize. We talked about the complex Laurent series, which was useful when we want a series expansion which is valid in a region outside the singularity circle of A. So remember, if this is our function, when we use Taylor series, if there's a singular point at A, then our expansion is only good for our center of expansion up until we reach the point A, and that circle, the radius of A, that's the limit of where we can start expanding our series into and have things converge. So with the Taylor series, we cannot use a contour which contains the singularity because the Taylor series requires that f of z be analytic at all points inside C. So in other words, when we integrated in order to find the coefficients, we could not use something that was outside of the singularity circle because the Cauchy integral formula requires all the points inside C be analytic. So what we did is we used the Laurent series. And for the Laurent series, we drew this interesting curve that totally avoided A. And then by deformation, we got this annular region. And what the Laurent series is, the form is the same as the Taylor series. It's a series. The differences are that it's a series with negative exponents, and then we go to positive infinity exponents, and it's c of n, some coefficient, times z minus z naught being the center of your expansion, raised to the nth power. Again, for Laurent, you have negative exponents. I like to separate it out this way, so my negative exponents, I express that by putting it in the denominator of the fraction. This is called the analytic part, since there's nothing that can be singular, so it's always analytic. And this part where we have the negative exponents, or the z minus z naught in the denominator, this is called the principal part. Then we have this formula here for our coefficient c of n, which is what we derive when we look at this formula and we integrate around c. But we didn't really emphasize calculating the Laurent series using this integration formula, because what we usually do is we use the basic Taylor series, much like we did in our previous video for the complex Taylor series. We brought back this problem that we worked in our previous video when we were talking about complex Taylor series, and again for the Taylor series we had to have z within the singularity circle of A. So this was the solution, and we then compared it if we want to get the convergence now with z possibly, or actually, absolute value z is greater than A. So we needed a Laurent series, and we worked this example here. And the last thing we did was our main example for this video was the Laurent expansion about z equals 0 of -1 over z minus 1 times z minus 2. And we saw that there were two singular points at z equals 1 and z equals 2, which means we have this drawing. We have our singular circle for z equals 1 and singular circle, for a equals 2. So we have F analytic for three different regions. The first one, when we're in this circle, absolute value of z is less than 1. When we're in this annular region, when absolute value of z is between 1 and 2. And finally, when we're outside the two circles, that is z is greater than 2. So we worked this problem. It was a little more detailed and involved than just a Taylor series. Finally, in this section of the book, we also had the topic of classifications of singularities, but I decided to make that a separate video, because this last example and all this other stuff is, it warranted its own video. So that's it for this video. Thank you for watching.